Hello all, I'm Dr. Angela Patrick and I would like to talk to you today about graphs, particularly the difference between quantitative and qualitative. So, as you can probably tell, not all data is created equal. Some data is qualitative while others is quantitative. Another way to separate data is to actually look at what is being measured. And to do this, there are 4 levels of measurement, as you already know. And different levels of measurements call for different statistical techniques. We spend a lot of time in statistics talking about distributions. And a distribution is simply a collection of data or scores on a particular variable. Usually these scores are arranged in order from smallest to largest, and they can be presented graphically. Because distributions are so important in statistics, I do want to give it some attention and show you several examples of different types of distributions and how they are depicted in graphs. So this is going to be the outline that I'm going to discuss with you today in summarizing qualitative data, summarizing quantitative data, and then we're going to look at the different distribution shapes and what do those mean. So in summarizing qualitative data, it can be summarized with something called using a frequency distribution. So all a frequency distribution is a table, and it summarizes how things are spread out. Don't get carried away by overthinking a frequency distribution, because all it is a fancy word for a table basically. And many times what we want to do is we want to figure out a pattern for a particular data set. So anything you want to measure by a number, we use a data set. And so what you're going to do is you're going to list all variable categories and make sure those categories do not overlap. And it will show the counts and the frequencies for each one of those categories. For example, it could be every member in a team, or a unit or a person, in that sample, it must be in a category. And then at the end, it's going to show a total. So let's look at a Jeep sales example. Let's just say, as you can see here, that we have 20 different customers who have purchased different models of Jeeps, right? So you've got Jeep Commander, a Jeep Grand Cherokee, Jeep Liberty, and a Jeep Wrangler. So that's what we can see so far. So we see 4 different types of Jeep models that 20 different customers have purchased. So in order to set up our frequency distribution table, once again, it's a table that summarizes how things are spread out. We're going to list all the variable categories. We're going to make sure that they do not overlap. We've got the Jeep Commander, the Jeep Grand Cherokee, the Jeep Liberty, and the Jeep Wrangler. And it's going to show us, how many counts or the frequency for each one of those categories. So, for example, we can go back here and count. We can look at, okay, so customer 1 bought a Commander. Customer number 5 bought a Commander. 6 bought a Commander. 8 bought a Commander. 13, 14, and 20 bought a Commander. So that's 7 different customers who bought a Jeep Commander. You see, if we look at our data set here for Jeep sales, I see a lot of models repeat, but I don't really see a pattern yet. So what we want to do now is we want to set it up in a frequency distribution, also known as a table. So remember, whatever your data set represents, you are going to title your column with that. So let's go back and look. So here we go. Here's a frequency distribution for our Jeep sales. There were 7 customers who bought the Jeep Commander. There were 4 customers who bought the Jeep Grand Cherokee, 4 who bought the Jeep Liberty, and 5 who bought the Jeep Wrangler. So all we're going to do, remember, we've got our titles, and then we're just going to add up. So what is total sales? It is 20. This is how many items are in your data set. And you always want to double check the items in your data set. So what's the benefit of the table? Well, I can tell you the most popular vehicle sold is, guess what? It is the Jeep Commander. So now let's talk about relative frequency and percent frequency. Relative frequency is how often something happens divided by all outcomes. Unlike frequency, relative frequency involves a very simple calculation. It's your percent. It is your frequency divided by your total. And then your percent frequency, all you're doing is it is just a percentage of actually how often it actually happened. So let's do this with our Jeep sales example. So we have our frequency distribution table here. We have our Jeep models of Commander, Grand Cherokee, Liberty, Wrangler, the frequency each one the sales occurred. So 7 Jeep Commanders were sold, 4 Jeep Grand Cherokees were sold, 4 Jeep Liberties were sold, and 5 Jeep Wranglers were sold. So the relative frequency, once again, is how often something happens divided by all of the outcomes. So if 7 Jeep Commanders were sold, what was the total? We're just dividing it by 20, and that equals 0.35. And then if we want to find the percent frequency, we're just going to multiply that number times 100. And so that is the percentage of how often it happens. So 35% is how often that Jeep Commander model was sold. So many times what we want to do after we have our frequency distribution table is we want to somehow visualize what this may look like. And one way we can do this is by putting it in a bar chart. So a bar chart or bar graph is used for words that use description. And what you'll notice is that for a bar chart, that the columns are not touching. And so we can see the different types of Jeep sales, based graphically by the bars. And so, of course, once again, the Jeep Commander was the highest one sold. We can also do this in a pie chart, which is very helpful, especially when looking at percentages. And so all a pie chart is just a circle that's divided into various slices where the size of each slice represents its relative frequency or percent frequency. And of course, 35% of all sales came from the Jeep Commander. And then we have something called a Pareto chart. And all a Pareto chart is, it's just a simple bar graph, and it lists categories in order from most to least frequency. So that's different than the bar chart, right? So a Pareto chart is going to, list the categories in order from most to least frequencies. So now let's talk about summarizing quantitative data. So let's look at this payment of time example. So let's just say a firm instituted a new billing system to reduce the amount of time between the time a customer receives a bill and the time payment is received by the firm. So we're going to look at the following slide that shows a sample of 65 times in days for randomly selected invoices. So here's our data set. Now, I can't tell a whole lot from it right now. So the first thing I want to do is set up a table. Since there are 65 data points, I want to determine a class width to actually narrow down my frequency table. So step 1 is we need to determine how many classes and the width. So let's just say that we want to divide this into 7 different classes. So in order to find the width, what we're going to do is we're going to take the largest data value minus the smallest and then divide it by the classes, how many classes we want. So the largest data value in the set is 29, and then the smallest is 10. So we're going to take 29 minus 10 divided by 7. That gives us 2.71. You always want to round up. So that's going to make our class width 3. So the first thing you want to do when you're summarizing quantitative data is step one is determine the class width. And so we said we were going to divide it into 7 different classes, so our class width is going to be 3. All right, step 2 is we want to find the lower class limit with LCL. So we're going to consider using the smallest data entry for the beginning. So the first lower class limit, so in the payment time example, it's going to be 10. So, and then we're going to next add the class width that we decided was 3 to the beginning point to obtain the second lower class limit. And we're going to continue until we have all the lower limits for each class. So in this example, our lower class limit for the second class, you know, hey, our class width is going to be 3. We're just going to add 3 to it. So it's going to be 10 to 13. For the third class limit, it's going to be 13 to 16. Okay, and I'll show this all in a chart here soon. So next, we need to find the upper class limit, the UCL. So we've got to determine what the appropriate UCL is. So when we're developing by hand calculation, a rule of thumb is to choose a number, you know, that is 1 unit lower than the following LCL. So in the payment time example, the UCL for the first class is 13 minus 1. That's going to be 12. For the second class is 16 minus 1. That's going to be 15. For the third class, 19 minus 1. That is going to be 18. So, you know, and then we are going to find the frequency for each class. So now you can see our lower class limit and our upper class limit. So we have our 7 different classes, 1, 2, 3, 4, 5, 6, 7. Our class width is 3. So 10 to 12 days, 13 to 15 days, 16 to 18 days, 19 to 21 days, 22 to 24, 25 to 27, so on and so forth. And then we're going to count, you know, what's the frequency that it occurred in each one of those classes. And so, and what we can do is we can set it up in a histogram. And really, a histogram is very similar to a bar graph, except that the bars are supposed to touch. The reason they touch is because it uses data values that are numerical. So looking at this would just be a bar graph, right? So in order to create a histogram, which, you know, a lot of times that we want to do, we have to find our upper class limit, our lower class limit, and put it together. So, and we've got to figure out our class boundaries. So a halfway point between a UCL, upper class limit, in one class and a lower class limit in the next class. In this example, what we're going to do is we're going to subtract 0.5 from the lower class limit, and we're going to add 0.5 to the upper class limit. And in order to, a lot of times we need to find the class midpoint, and this is used for estimating the average value in each one of those classes. So all we're going to do is take our lower class limit plus our upper class limit and divide it by 2. So, you know, what we're looking for the lower class boundaries and our upper class boundaries. So the boundaries are where those bars would meet, and we want this information in order to see where it would touch on a histogram. It is used to determine in which interval an actual observation falls. All you do, once again, is you're going to take 0.5 and subtract from the lower class limit and add 0.5 to the upper class limit. So, and here's an example of what that would look like. You know, many times we want to do a frequency polygon, so we would also need to find the class midpoints, and it's used for estimating the average value in each class. As I said before, where we take that lower class limit plus that upper class limit divided by 2. And so our class boundaries right here, this is where I was saying you subtract 0.5 and you add 0.5 to make that histogram where the bars actually connect to each other, that's what would create that. All right, yeah, so here's the frequency polygon. And this is, where we use those class midpoints. So, yeah, so the dots on that are the class midpoints. So that's just that lower class limit plus that upper class limit divided by 2. That's all that is. So this is called an ogive. And sometimes it's called a cumulative frequency polygon. It's a type of frequency polygon that shows the cumulative frequencies. In other words, the cumulative percents that are added up on the graph from left to right. So an ogive graph plots cumulative frequency on the y-axis and class boundaries along the x-axis. It's very similar to a histogram, only instead of rectangles, an ogive has a single point marking where the top right of the rectangle would be. It's usually easier to create this kind of graph from a frequency table. So now let's talk about distribution shape. So, when graphed, the data in a set is arranged to show how the points are distributed through the set. These distributions show, how spread, the dispersion, the variability, the scatter of the data. And the spread may be stretched covering a wider range or squeezed, covering of a narrower range. So the shape of distribution is described by its number of peaks and by its possession of symmetry, its tendency to skew, or its uniformity. So distributions that are skewed have more points plotted on one side of the graph than the other, which we'll talk about. So as you can see in this top one, a symmetrical shaped graph, it's got that pretty bell shape. We always talk about the bell curve. So when graphed for a symmetrical shape, it's a vertical line that's drawn at the center will form mirror images, with the left half of the graph being the mirror image of the right half of the graph. In the histogram and also dot plots, this, once again, shape is referred to being a bell shape or a mound. The most typical symmetric histogram or dot plot has the highest vertical column in the center, right here, and the shape is often referred to as being a normal curve or normal distribution. Not all symmetric graphs, however, have this shape. Okay, so now let's talk about the uniform distribution shape. So as you can see, the data in this type of graph is spread out equally across the range pretty much. There are no clear peaks in these graphs, and considering that each data appears the same number, pretty much the same number of times in the set. So it's got this clear, it's almost straight across, but not exactly. You can see the big difference between this nice pretty bell curve or mound compared to the uniform distribution shape. So let's talk about right skewed, or it's called positively skewed. Here, we have fewer data plots are found to the right of the graph. Gives a nice little tail here toward the larger numeric values. And the tail of the graph, what you can see here, is kind of pulled toward higher positive numbers or to the right. And this, the mean typically gets pulled toward the tail and is greater than the median. Of course, there may be exceptions to this as well. And let's talk about the left skewed or negatively skewed. Here, what we have are fewer data plots that are found to the left of the graph, especially toward the smaller numeric values. And you can kind of take your hand and you can kind of pull that tail to the left, or even in the right skew, take your fingers and, pull that tail to the right. So the tail of the graph on the left skew is pulled toward the lower or negative numbers or to the left. And the mean typically gets pulled toward the tail and is less than the median. Of course, as I said, there are exceptions to that rule as well.